we're recording now, so be careful what you say. It'll be recorded. We can't use.
Windows the makeup artist.
Okay, hello.
Hello.
So how's it to be back on campus?
Well, it was, personally I really enjoyed it. Just being able to see students again, I was teaching abstract algebra last semester. But not many students were still not back to how things were pre-pandemic, but just having that sort of social interaction, being able to just chat a bit before and after the classes, I think is something that most people, like lecturers and students, missed. So I'm really hoping that we're going to go to more and more interaction.
So what is some useful advice that you have received and would give your younger self?
So something I've been told actually rather late at the end of my PhD when I was applying for postdocs and all that was to try to communicate your mathematics as clearly as possible, which sounds like an obvious advice, but it's actually something that you don't necessarily think about often enough. Communicating mathematics is hard, maths is hard in general, and it really pays off to be able to take a step back and think about how you want to structure what you want to say, highlight the key ideas, and that's something. It's as a student, it's really useful for you because being able to get the big picture is a really useful way to check that you actually understand something deeply. But also from a more utilitarian viewpoint, being able to explain something clearly to someone is a good way to get others interested in your work and start new collaborations, or when you're applying for jobs, being able to explain why what you're doing is interesting is extremely useful. So that would be my main advice.
What is a common myth about your profession that you want to debunk?
I guess I would have to go with the mathematicians being solitary people. We're spending, of course, a lot of time on our own thinking about maths and all that, but there's a real important social aspect of working with others. For instance, most of my work in the past few years have been purely with co-authors in the UK or in Canada or in Poland. So it's something quite important to emphasize that you're not, or if you choose to, you're not just on your own thinking about maths, but you've got lots of other people, there's a whole community to work with. And so that's why we meet at conferences, or sometimes just at a day in Glasgow or Aberdeen or whatever, to try to interact with others, teach each other new mathematics. And it's really that social aspect that I think a lot of students may not be completely aware of.
Okay. And what are some useful resources for students who want to dive deeper, and which help you along the way?
I guess there's a difference between when I was a student and now, because now there's everything online much more than when I started. So if you want to dip your toes first to learn about new topics, there's a lot of resources online, whether channels on YouTube or online magazines like Quanta magazine or Chalk Dust, for instance, or even social media like Reddit. There's a big maths Reddit. But if you want to go a bit deeper, there are online courses, of course, but I guess books are the main resource. There are lots of books on lots of topics. So my advice to you would be to actually talk to your lecturers, because we know you, we know your background. So we'd be able probably to give you some ideas of some books that could help you learn about some topics. It's great for us as well. I mean, I personally really enjoy when some student comes along and say, "Oh, I really like that topic. You said it was connected to this application or whatever. Is there somewhere I can learn about that?" I mean, personally, I love that, being able to help that way.
So having said that, is there any book that you recommend any mathematician must read?
Any mathematician, that's maybe a bit too much. I don't think there's one single book that is useful or important for everyone. There's probably a book for a given topic that is considered the main resource. maybe something a bit different, like some essay, short essay, so don't worry, it's like less than 20 pages, that I read, I think, when I was a first year PhD student. Was an essay by William Thurston, an American mathematician, which I think was written about 30 years ago now, and it's called On Proof and Progress in Mathematics. And it's almost a bit philosophical, and it's a reflection on kind of the psychology and sociology of mathematics and mathematicians, like thinking a bit about what it means to prove something, why we prove things in mathematics, how we communicate mathematics. And these are all questions where you think, well, I know the answer, but when you start thinking about that, you realize it's a bit more subtle, and these are actually quite important and interesting questions to think about. And I always think that it's quite interesting to like take a step back and not just like do what you do, but like think about why you're doing what you're doing in the way that you're doing. So
yeah. Any mathematician that his or her work inspired you along the way?
So I'm gonna say one, but when I say a mathematician who like inspired me, I'm not necessarily talking about the person itself. I'm generally not that much into like the story or the drama surrounding a single mathematician, but more about the mathematics they created and like the mathematical ideas. So for me, I guess that would have to be Galois, so Évariste Galois, a French mathematician. So it's not really connected to my work. I don't work in Galois theory, but I learned about a bit of Galois theory when I was at first year of uni. Because I knew from high school that you've learned about how to solve polynomial equations of degree 2, you've learned the formula, and I had learned somehow or read somewhere that if you go to higher degrees, all of a sudden it becomes impossible to solve some of them, and I wanted to understand why. And so I think that that work had a big impact on the sort of mathematician I became. On the mathematical side, that was the first time where I saw this idea that to understand an object, it's really useful to understand its symmetries. So if you want to solve, in that case, a question about the roots of some polynomials, looking at the symmetries of polynomials, which was an idea that was completely new to me. I had never seen that in high school before, at first year of uni until then. But at the kind of meta level, was also something quite interesting, is that until then, mathematics in high school is essentially computations, right? You learn about how to solve certain problems, how to apply certain algorithms to do various things. And here was a problem which was about showing that something is impossible, not about computing anything, but showing that something cannot be done. And I had no idea how you were supposed to do something like that. And so that was the first time that I read about some mathematics that, instead of focusing on computations, try to actually reveal the sort of hidden structure and sort of hidden relations that govern certain mathematical objects. And so that really had a big impact in that I tried from then on to focus on some maths that kind of go a bit away from computations, but focus more on like the abstract structure around it.
Right. We hear a lot about pure mathematician and applied mathematician. Is there any non-obvious difference between them?
I don't think so, actually. I mean, there's the obvious difference that applied mathematicians tend to focus on questions that come from the real world, like modeling like the spread of a virus for something a bit current. But apart from that, it's not. I don't think there's such a clear distinction. So just to give an example from like where I'm from, so I work in group theory, and I'm definitely working on the pure side of group theory. So I care about questions that are just framed within mathematics without any sort of motivation from the outside world. That being said, there are people trying to use group theory to develop new encryption protocols, or maybe like the RSA one using prime numbers and their properties. And some people are trying to use properties of groups to do that. And when you start trying to understand how you would go about developing such protocols, there are lots of very pure questions about groups, phrased purely in the world of groups without any reference anymore to the sort of application. and all of a sudden you're doing pure maths, even though you were like completely motivated by something applied. So that's something that tends to happen quite often. A lot of maths, even pure maths, came from very concrete questions, and so it can happen very often that you have an applied mathematician who might have to develop like new tools and new pure tools to be able to solve their problem, and you might have pure mathematicians by training that might realize that there's a connection between like the sort of pure questions they like and some concrete question, and they might start working on that. So I don't think there's such a clear distinction. I don't think there's an obvious difference between the two types of mathematicians.
So when do you believe students can call themselves mathematicians?
Right, okay, so that's a tough one. So I'm going to put my mathematician hat on. You would have to first define what it really means so what's a mathematician? And it's not completely clear, right? It's a bit like what's a number? Like, you think you know, and then when you start actually trying to think about the definition, it's like, how do I do that? And it's a bit the same for mathematicians. It also seems to depend on the country. But so instead of what is a mathematician, maybe more interested in what a mathematician does, and to try to stay a bit vague. A mathematician is someone who probably spends most of their time, or working time at least, thinking about mathematics, engaging with mathematics, trying to use mathematics to solve some problems, applied or not, maybe having to read new mathematics and learn new mathematics, or have to teach mathematics to some colleagues every now and then. So essentially, as a student, if you kind of recognize yourself in that sort of loose description, I'm perfectly fine with you calling yourself a mathematician. I don't think there's such a clear-cut definition, unless you mean professional mathematician. But if you just think about the word mathematician, I think that's loose enough so that many students can call themselves that if they wish.
Okay. So we see some that finish a maths degree but still not sure which area is their area of interest. Do you have any suggestions?
Well, I would say that it's not surprising actually, right? I mean, after your undergrad, it's like 3 or 4 years after starting uni. You're still quite young mathematically. You've seen a few topics already, but mostly introductions, and it's quite hard to already know at that early stage what it is that you want to do for like a significant amount of time after that. Like in my case, for instance, after my undergrad, I had some idea that there were some topics that I enjoyed and others that I didn't, but nothing really like very narrow. I didn't know I want to work in that field. So maybe you know already that, for instance, you like stuff to do with geometry, or you like interactions with computer science, or you like the motivation of knowing that you're working on applied problems, for instance. These are things that you might already know at the end of your studies. But after that, so my advice would be to kind of keep digging, in a sense. So ask your lecturers if you know that, for instance, you enjoyed the course in like linear algebra or functional analysis. Ask them, what it's like, what research can look like in that field, if they have resources for like more advanced courses to see a bit what it's like, because there can be quite a significant difference between introduction level topics that you're being taught here and what it looks like a bit later at the master or PhD level. But it's not at all surprising that you don't know yet what you want to work on, work in. I did a master's in algebraic topology. I knew that I enjoyed like this idea of topology and geometry, so understanding the shape of things in a very loose sense. But in the end, I'm not working in algebraic topology. I'm a group theorist. I'm working in geometry group theory. So you keep kind of navigating those mathematical waters. What's important is to know where to look for like more material to refine your tastes.
Okay. So what are some misconceptions about a maths or a maths degree, and how would you combat them?
Right, so I guess the main misconception actually comes from the way students are taught maths in high school. So in high school, there's a lot of emphasis on being taught to the test. right? So in particular, a lot of mathematics is about learning those formulas, those algorithms about how to solve given problems. Almost becomes a bit Pavlovian, like you have to do this, press that button. So students come with the expectation that mathematics is about like those formulas and those algorithms, but not so much about understanding why this works. There's not that much of an emphasis on proofs and understanding why these recipes actually work, which is something that becomes much more of a focus at the university level and in advanced mathematics. So that means that when students arrive here, especially when we start like learning about those more abstract topics like linear algebra or abstract algebra, you've been through that not so long ago with me, it can be quite a bit of a shock for students, because presumably they chose a maths degree because they were like good at mathematics and they enjoyed that, but to some extent they were good at something that is, or they're being told that it's not longer what mathematics is really about. There are courses that still have some emphasis on computations, that's clear, but there's a shift towards like understanding and proofs and being able to justify your reasoning. So that, I guess, is the main thing to understand when you go into a maths degree. And as to how we kind of tell students that this is how it actually is, well, I guess as lecturers we try to emphasize that in our courses. We try to emphasize that in the way we assess, like asking proofs. I know that a lot of students complain about how much proofs are in my exams, but there's a whole lot of mathematics that you have access to once you're able to like justify your reasoning. And to me, I mean, if maths was just about essentially pressing a button, I would find that rather soul crushing. Like being able to just answer those why questions and really understand why things work, I think is really what mathematics is about and why it's so fun.
So having said that, is there any question that you're most tired of hearing, and what would you like to say about it?
Is that going to be at the exam? No, I'm kidding. Okay, although that comes up a lot, but okay, now that's a more serious question. So I guess, I'm going to talk about the question that I'm asked more at the uni, although it's a question that can be asked in general, which is like, why is it good for? Why is it used for? So for like the general public, I think it's very important that we're able to explain why mathematics can be useful, etc., especially since the general public is funding universities and mathematical research in general. But here I want to focus more on like math students, because also sometimes, quite often, math students ask me those questions. And I'm perfectly fine like emphasizing the applications. Like, so for instance, I teach abstract algebra in particular. I'm perfectly fine emphasizing the applications. I've supervised fourth year projects on like error correcting codes, or even some board games that use some abstract algebra. But I think there's something to be said about not trying to only justify mathematics by its usefulness in the real world. I think mathematics has this dual thing of being an extremely powerful tool for like concrete problems, and also something, I'm not going to go into like is maths an art sort of debate, but something a bit more part of the human cultural heritage, in a sense, right? A bit like music, which is something that people have been doing for a while, can spend their lives working on because they enjoy that and they find that extremely meaningful. So I think it's important to be able to also emphasize the kind of cultural value of mathematics, and not just the ultimate more like economic worth. So like, instead of just like, why is it good for, I would quite enjoy if like students were not only asking that, but also more questions, more like, like what else is there to see, or do you have more like fun facts about this topic to tell us about?
And in the end, is there any piece of maths you'd like to tell us about?
Yeah, so I work in group theory, but I'm not going to be telling you about group theory because it's maybe not as accessible, especially in the very short time we have. Some piece of maths where I had a bit of a wow moment the first time I saw about it comes from a very simple question, which is generally called the Buffon's needle problem. So it's one of those problems like the four-color theorem, where the people who thought about these obviously had too much time on their hands, but still it's a fun problem. So you have to imagine you have some floor made of strips of wood, all 10 centimeters wide, and you have a needle, a straight needle, which is also 10 centimeters wide, and you throw it. Just assume that the floor is infinite for simplicity. You throw it on the floor, and you ask yourself, what's the probability that the needle is going to cross one of the lines of the floor? And there's a very nice and simple answer. The answer is 2 over pi. And then the question is why, and how do you prove that? So there's a direct way. You model the problem, so you have to compute some density function, and then you have to compute some integral and do the computations, and at the end, boom, 2 over pi appears, and you're happy. But there's a slightly different approach, which I thought was completely mind-blowing the first time I heard about it, which is to kind of change the problem a bit, and it's going from what's called the Buffon's needle problem to what's called the Buffon's noodle problem, which consists of essentially bending the needle. So imagine for a sec that like instead of one needle, you can look at some sort of line that is made of several different needles. They might make angles, or it might just be a straight line. And instead of asking yourself, now what's the probability that it's going to cross a line, is what is the expected number of times that your curvy line is going to cross those lines. And when you start thinking about that, so it's a more general problem that in particular will give you the solution to the original problem. But when you start thinking about that, there's some new structure that appears. In particular, if you put 2 needles together, it does not depend the sort of shape it's going to have, whether it's a V or whether it's like a new straight line. The answer is only going to depend on the length. And that has to do with some probability concepts, in particular linearity of expectation. And once you've realized that, you realize that the number of crossings is just going to be proportional to the length of your noodle. And so now there's a very simple way to find the answer by taking a particular shape for your noodle that always going to cross. Whichever way it falls on the floor, always going to cross the same number of times. And well, I'll let you read about that, but since the answer involves the number pi, you probably have an idea of the sort of shape that you're going to have to look at. And you get, again, that answer of 2 over pi. So it's a completely different approach. And in a sense, if you try to transform it into a purely formal proof, it's more involved. There's more math there. But what I find, there are 2 things that I really like about it. The first thing is that you've got some sort of narrative. Once you've understood the sort of story that's being there, you're not going to forget it, right? I can tell people about that, like in 2 months or in 1 year, I remember how it works. The computations from the first approach, have to think again. It's like going to be an arc sine or something like that. So there's that being able to focus on, the big picture, like the key idea, and have some sort of narrative, which I think is extremely satisfying because you can wrap your mind around that proof. And also the fact that something that's quite that happens in other problems in mathematics is to essentially make the problem harder at first by looking at like curved needles in a sense, but ultimately simplifies the problem because you've uncovered additional structure that you can use and additional tools that you can use to make the problem almost trivial at that point. And I think that's extremely nice to see that. So you can, there are lots of resources online. If you search for Buffon's needle, Buffon's noodle, you find the 2 proofs and have a look at them and compare them. And personally, I was absolutely amazed when I saw that second.
Thank you so much.
Well, thanks for having me. I hope I'll be able to see you around more regularly and hopefully discuss some more fun maths with you and other students.
If you do want to look over here, it's probably best to look into the camera here. So if you do want to address the audience or anything, right, like look into here rather than...
Would it not be odd to look into the camera when
Well, I just mean like, I don't know. I don't know what. I don't know.
Very good question, Mazal.
Very good question.
Looking straight at